Hello, my name is Steven. Welcome to Hyfindr Tech Talks, where it is our goal to understand the technology that makes the hydrogen economy work. At the end of many of the things that are implemented is electricity, and that has to be at the right current. For that, DC-DC converters are needed, or other kinds of converters. And today I'm very, very pleased to welcome a man who is somewhat of a legend in this field. He founded a company 34 years ago all around this topic and has run it ever since. He's from Aradex, which is a brand that some of you already know. And I'm very pleased to welcome Thomas Vetter. Hello, Thomas.
Hi.
Welcome. It's nice to have you here. And I see you did not come alone. I see you brought your big body with here, which we could hardly get on the table. What is this, please, Thomas?
Yeah, this is a DC-DC converter. You may know it from AC grids. You have a transformer to transform the voltage to the right level. But in the fuel cell makes DC voltage, DC current.
Direct current.
So you cannot transform it just by using a transformer. For this, you use a DC-DC converter. So that's the function inside to make one voltage, to shift it up to the voltage we need.
Okay. So to the voltage we need. And so, I mean, as designers of fuel cell systems, we've seen that that depends on the number of cells. Why do we even have to take this voltage up or down?
Yeah, normally you want to have a fixed voltage on the target side, normally given by a battery, for example.
Yes. Mm-hmm.
And this voltage, what I see as a trend on the market, increases. Some years ago, many systems were 400 volt, from the passenger cars. In the trucks, we see 600 or 650 volt. Now we see the trend going to 850 volt. And to show you the reason for this, I have two cables with me. This is a cable you have to use for 180 kilowatt power. That's what's also the power of the DC-DC here. Mm-hmm. And when you have a battery of, let's say, 600 volt, you need for the DC wiring and the wiring between the inverter and the motor, such kind of cables.
Yeah.
And what we see, you can reduce the cable to use a smaller diameter. So it's easier to bound and cheaper and lightweight. So if you compare these two cables, you can see it here.
Yes,
this is 70 square millimeters inside. This is 50 square millimeters. So this is cheaper and easier to put into the truck. So we see the trend of upcoming voltage, so let's say the level of 800 volt.
800 volts, okay. Yes, I mean, we know this from a lot of electric vehicles and these kind of applications that you take out, you open the bonnet or you see them and then you have these orange cables which are specially marked for the current. And obviously, if the cables can be thinner, then that's worthwhile. But this isn't exactly small, so, and this probably also costs some money. Is it therefore a business case really to get a bigger one of this and for that get smaller
It's
cables?
not a bigger one, it's just we have to change the function. Mm-hmm. So for the fuel cell voltage, it is lower, the target voltage is higher, so we speak, this is a step up.
Yeah.
A step up device. So to move the voltage from the fuel cell level to the target level. And the size, normally, if you make your job as an engineer, is not dependent on the step-up ratio. So this had the step-up ratio up to 7, that's much. Normally in the market is 3.5 or 4. But the size does not increase. This just the size is given because we have 180 kilowatt continuous power, so it's really for big trucks, big fuel cells.
And step-up ratio of 7, that means so coming in with 100 can go up to 700 volts, is this correct?
That's exactly that.
So,
because we see on the other side that the fuel cell voltage, to lower the cost, goes more in the direction to higher current and lower voltage, because bigger plates but less of them is cheaper to produce. So on the one hand, the target voltage increases, on the other hand, the incoming voltage, the input voltage goes down. Mm-hmm. So the step-up ratio must become higher. That's the challenge. Okay,
so a lot of us know how to transform current from AC to AC, as you've already mentioned. So that's easy with the coil. But a DC-DC converter, what is inside this box and how does it actually work? Maybe you can help us with that. Yeah.
We have a simplified schematics here.
Yeah.
On this side, we see the fuel cell is connected, then buffered by a capacitor to smoothen, if something is switching, to smoothen everything. So the energy is firstly stored in this input capacitor. Then we see here what we call a storage choke. That's an inductivity in the physical way. Here is the switching transistor. When this transistor switches on, so makes a short circuit, but not really a short circuit because the inductivity is here, then we have an increasing current from this capacitor through this choke here to 0. And when the current is high enough, then the transistor, we switch it off, but the current wants to keep the flow. That's what we call the law of Mr. Lenz. It was a physicist many years ago. And then the current wants to keep his flow. So, but the transistor blocks, so it must take the way through this diode into this capacitor. So then the current flows and charges this capacitor, then the voltage of this capacitor increases. And you make then again a short circuit, then release it, make a short circuit, release it. And this kind of switching on and off of this transistor, that's the function of this conversion. So the time on time and off time and the frequency, this you must decide. You measure the voltage on the output, you measure the voltage on the input, and then the system must decide the switching. That's what we do inside in the control logic.
So this is a boost setup?
Yes.
And so if we're coming in at 100 here, we could come out here at 700. And what does the 700 depend on? On how fast this one switches, or how big this was? How do you make it do 700? How could it do 500? What do you have to change?
It's depend on the capacities, but especially the inductivity and the switching times.
Okay. Of this storage choke. Okay.
Yeah. And one of the specific things is to make the switching frequency higher. Can be done by at the moment available silicon carbide devices. Okay. Because when you make the switching frequency higher, you can make the storage choke smaller.
What kind of frequencies are we talking about here?
In our last device, so what's in the series production is only 6 or 7 kilohertz, but now we are on 80 kilohertz. 18 kilohertz. 80. Okay. So more than 10 times more.
Okay, more than 10 times more. And that's what we're coming to see on the market. 80 kilohertz of switching. Yeah. All right, okay. Yeah, perfect. So is there more to know about this?
Yeah, as I told you, when I make the switching frequency higher, we can reduce the size of a storage choke. I have just one device here with me.
Yes, so this is a storage choke.
That's the storage choke. You see here the copper inside and the wires.
If we put it here, then we can see it good. Yeah, exactly there.
And
yeah, that's fine. It can just be where it was.
the trick is you make the copper. You make the choke smaller, so you need less copper.
Yes.
It's not primarily to save copper, but if you have less copper wires inside, then the losses are reduced. So you can really increase, that's really strange, you can increase the total efficiency with a higher switching frequency if the switching device is good enough.
So because I was just asking, why can't we go even higher? I mean, we see the guys who do the inverters, they go to
You can also go higher, but you have to balance it because the switching losses in the device also create losses. You have two main losses, the switching losses and conductivity losses in the transistor, and the losses inside this choke. So you have to find the balance which makes the whole system in the best way.
Okay. So speaking of balance, and you say losses, I know that efficiency is a bit of a topic in this.
That's really the topic. We calculated before we make the construction here of this device, the layout, we set some target values. And one of the target values have a better efficiency than our last product. To give you a feeling, when you have 1% higher efficiency, and that's what we got with this device in a typical logic, 1%. You save 1% of hydrogen in a truck every day. So if you calculate the truck runs 1 million kilometers and takes 1 kilowatt hour per kilometer, big one, 40-ton truck. Then it's about 5,000 euro in 1 million kilometers you save on hydrogen cost.
Okay. Oh, that's considering that trucks get sold by also these kind of values, and you have different kinds of efficiencies here.
Yeah, this depends on the step-up ratio. So if the fuel cell runs at 300 volt, that's the green line.
That's the okay.
Then the efficiency is really even 99%. That's not
99% efficiency.
That's not a drawn curve, just fake, but this is really measured. So this is typical for a 180 kilowatt version. If you have, let's say, a 120 kilowatt version, and with the same current, you have, for example, input 200 volt, then we have also between, let's say, 98.6 or 98.4.
So just looking at this, we are moving between 96 and 100% of efficiency. So this is like, just a wire going through, it would be 100% efficiency. So this hardly takes off any. If you will. This is great news overall. And when does the efficiency go down?
When the voltage is down. So if you only really have 120 volt
as input,
and you have to step up to 700, then the job is harder to do, and the losses are higher. But even there, we are in the range of 97%.
Okay, so that means the higher the job this has to do, let me say, the less the efficiency. Okay, and so. I know that inside here we have several of these. Maybe can you just take us a little bit more inside the box? Yes.
This is one. This device. So we know this is the choke.
Yes,
here,
that we had. Yes.
Then we see here the transistor and the diode.
Yes.
We have 4 of them, and make an what called interleaved switching. So each of them runs at 80 kilohertz.
Yes.
But by interleaved function, we have then 320 kilohertz even in total, because we make one, then the other, So it's like a 4-cylinder motor. It's not all made the same, but one after the other.
All right.
So 4 of them is made to have a 125 ampere module.
Okay.
And if you take 4 of these, so 16 of these inductivities, then you have the whole device, what we see here, for 500 ampere.
Okay.
And if we take 8 of them, we can scale up to 1,000. So we can really scale the product.
The product, okay. As I see...
You see the different colors?
Okay.
Every color is this block, of 4 of them, and just one of this bubble is one of these switching devices. So we have 16 of these inductivities.
So that means what we have here is one of these blocks will be one of these setups that we have here. And then we have 4 here. Then we have basically these 4 blocks. And all this is in this setup, which where you can actually see. If we can, I don't know if the camera can show this, but we have these connectors right up front here, which are exactly the ones that we've also seen on the device. So that's the way it's set up. Out of curiosity, what is this big round thing?
You cannot switch off on and off the DC-DC converter to a fuel cell at the same time on the battery, because the battery voltage is there, the fuel cell voltage is there, but you have a difference. If you switch directly hard on, then you will destroy all the components. So you need what we call a pre-charge unit. And normally this is built outside, but then our customer must do it in his truck. So we make it inside. So we have a pre-charge relay, a main relay, and a pre-charge resistor, everything inside. But you see the big one, that's the main relay. So these devices are integrated to make it easier to mount the device into the truck. So it's a little bit of the size is the tribute that we put some more functions inside.
All right. That's very interesting. So, so essentially this device is a multiple of that little switching circuit. Is there more to know?
Yeah, what we see as a trend, because the current goes up and up, we see fuel cells on the markets, they will reach, let's say, 900 to 1,000 ampere in the near future. So you must offer a scalable solution, and 1,000 ampere, you cannot use this kind of cables. So you need copper rails. So what we expect is that the DC-DC in the future will become an integrative part of the fuel cell stack directly. And because we have the current control in this high switching frequency realized based on what is called FPGA technology. So we create our own chips, I would say.
That is for the switching.
That's for the switching, and also for the closed loop control. It's very, very fast. And as a result, we can use this very fast control for, let's say, some more high-level functions.
Okay, okay. So, what does FPGA actually stand for, or maybe you can just say it a little bit for?
It's Field Programmable Gate Array. That's the. But what we do is really to create our own processor. We don't buy an Intel processor, but we make our own.
Okay, and you brought a slide to show that.
Yeah, one of our the demonstrators, we use an inverter and a motor to make music.
Yeah.
Really, to make music
okay.
near to high quality. That's completely senseless, but we can do the fast control. But for the DC-DC converter, we can use this, and this is known in the it's not nothing invented by us. It's called Electro Impedance Spectroscopy. We make sound pulses into the fuel cell. Yes. So we take the current out and modulate some small amount of sound inside. And then we listen to the answer of the fuel cell. This sounds strange, but really this is not invented by us. This is in the field of the research. This is well known that you make a modulation to have a look inside the fuel cell, and you can then find out the humidity of the membrane, for example, or other things, or state of health.
Through
of
the
fuel
reflection
cell.
of the sound?
Yes.
Okay.
You modulate the current, and you look to the modulation of the voltage. Both, anyway, we measure it, and we are fast enough, so we can do it directly with this high power device to listen what the fuel cell tells us. And this gives us the data we hand over to the fuel cell controller, and then they can adjust the balance between hydrogen and oxygen more precise to lift up the power a little bit.
Okay. Wow. Okay. That sounds really interesting.
I think a little bit more power just by software.
So
that's the trick.
Okay, and by listening to the fuel cell, and you emit a signal into that. Okay. Wow. Okay, and so you clearly see a trend of the DC-DC converter moving even closer to the actual fuel cells for this reason that they...
For two reasons. One, to integrate it because of the big copper rails, and to combine the controller, the real-time control of the DC-DC with the real-time control of the fuel cell to build a synergetic combination to make such advantage, let's say, added value functions.
When do you see this coming to market?
I think 2 or 3 years it will take.
Oh, wow. Okay. So that's okay.
Well, what I expect.
Then I think the good news is that we can still do a video on that when that comes.
Sure.
Because unfortunately, we've come to the end of our time. Thomas, this has been extremely interesting. I mean, who would have guessed that a DC-DC converter is on the way to getting so close to the fuel cell that it listens to it and adapts accordingly? This is almost bioscience that's coming up there. Thank you so much for explaining this. Thank you for your time. And thank you very much for watching. If you enjoyed this, please give us a like. On Hyfindr.com, you can find more components like this, everything around the hydrogen and fuel cell economy. You can get in contact with people like Thomas to make things work. We want to make you successful. So if you like this, please drop us a note or like us or watch another video, which we will be sure to make. Thank you very much for your time, and thank you very much, Thomas.
Thank you as well.
All the best.
Bye.